We saw yesterday a theorem just stated without proof about what kinds of surfaces you have in the universe. The classification of all surfaces due to a 19th century mathematician called Möbius. And according to that, we had two types, two sequences of surfaces. The sequence that we called sigma, those were the orientable ones, and sequence that we called nu or n, non-orientable ones. Sigmas were connected sums of tori, lots and lots of handles. Nu were a little more weird. You had a sphere, you took out a number of holes and you put the lids back in, but not ordinary lids, rather Möbius strips. Oh, nice sound effect. Are we supposed to go out? They keep testing alarms, but I mean, if the alarm is going all the time, then when the alarm sounds, people will think that it's been tested. false alarm. Okay, so that's the classification. However, did you wonder about this? Suppose that you have both handles and Möbius strips. Some surfaces like this, yeah, look like a mixture of sigma and nu. Question then, where does it fit into the classification, in the classification of surfaces? Which was stated in the theorem 19. Yeah. It should be just a bunch of handles or just a bunch of Möbius strips, but there might be a mixture. So how do you do this? Now we shall discuss a very beautiful technique, wonderful technique called handle sliding. In order to discuss that technique, we need a lemma. That's number 21. Here's lemma. Let's consider the simplest kind of mixture. That is when you have one handle and one Möbius strip. And we would want to know what this is. It turns out that this is homeomorphic to just 3 Möbius strips. And what do we call a surface like this? A from yesterday? N of what? N3, N of 3, that's right, N3. So if you have a sphere, make a hole and put in a Möbius strip and attach a handle, that surface is homeomorphic. So topologically the same as a sphere with 3 Möbius strips put in, it turns out. And that's the key lemma. Let's prove this lemma and then we'll proceed to the handle slide. The way we do it is the following. Let's imagine that this handle can be moved on the surface. We can slide it all over the surface. Here is the picture. We grab the handle. And then we try to move it. Seize the handle and slide it onto the Möbius strip. Okay, what's going to happen? Well, first imagine that there's no Möbius strip here, and then I grab a handle, can you see? And then I slide it, and then you come back to where you started, the same handle. There's no mystery about that. But when you go over Möbius strip, something magical happens. This is one of those magic zones where lots and lots of strange things happen, and when you come out, you are no longer the same. Here's how it goes. When you go in, this Möbius strip, which we are symbolically denoting by this cross picture, is in fact a more realistic picture, which you're more familiar with. Looks like this, doesn't it? Yeah. That's what happens when this handle arrives on the movie strip. This is the handle sticking out from the outside, and that's now attached to the part of the surface which is the movie strip. Let's slide this handle all the way around the movie strip once. What's going to happen? Well, next picture is going to be this. The handle comes here. It's sliding and sliding. You see? And then you keep sliding it. But you see, when you slide this handle, do you see what happens? The handle comes over on this side. Yeah? So whereas I was on this side, the handle comes over on the other side. I'm coming out from the outside, and then, sorry, I come around this way. So the next instant, we get the attachment of the handle, which will be over here. Okay. And then I keep going. I just keep sliding the handle. And amazingly, when you come out of the movie strip, the fourth picture, the handle is now attached to the other side of the movie strip. I hope you can see when I arrive. Whereas I started from one side, it emerges on the other side. Because I went around the movie strip once. It's like running your finger, and when you go around, movie strip being one-sided, whoop, you come out on the other side. So, then I go out. Okay? Then I go out of the movie strip. Around the movie strip, once. Yeah. Okay. And now come out. The result is, I'm going to draw it here. Instead of having a picture like that, now the handle is attached to the other side of the surface, like this. And this picture should seem familiar to all of you from yesterday. Look at the right half of the picture. That is one of the pictures of the Klein bottle, which we discussed at the end of yesterday. This side, there's still that same movie strip which is sitting. Yeah. So this half is a Klein bottle. And do you remember what the Klein bottle is in terms of movie strips? We can draw this picture of the Klein bottle. Which, by theorem, which example was this? We discussed it by example 20. Is a pair of movie strips. Yeah. So the conclusion is that this picture can be replaced by this picture, so the whole thing was 3 movie strips. End of proof. Huh? Very curious kind of proof. We have never seen a proof like this, but it's completely rigorous and indeed very useful later on. To show you the first use, now we have the possibility of doing arithmetic. That is, when you learn arithmetic, you have a table of multiplication. 3 times 4 is 12, and 5 times 7 is 42, 35, and so on and so on. Well, let's have a table of connected sum. It's like the table of addition. Here it goes. Well, what can you add? Well, all you can add ever, according to the classification theorem, is either sigma or nu. So you might consider adding sigma g to, say, sigma g prime. That's another g. For example, sigma 2 to sigma 3. Or maybe nu g to sigma g prime. For example, nu 4 to sigma 5 or something like that. Or indeed, you can add nu to nu and so on. So we have to understand what the results are for all of these. Some of these entries are very easy. What do you think we get if I add sigma, if I take the connected sum of sigma g and sigma g prime? Of course, you just have g handles, g prime handles. Together you get on the sum of the handles. That's all. How about nu g and nu g prime? Well, similarly, as Shima says, it's just this. The only tricky parts are those two entries. Yeah? But that we can do by the, using the lemma. Okay. So this is the table connect sum. It turns out that this entry, in fact, I can try to do the calculation in my head if I'm brave, g plus 2g prime, it turns out. So you are not adding g and g prime, but you double the sigma bit of the prime. And similarly, here it's symmetric. So g prime plus 2g. Okay. So you almost always get nu. So 3 entries out of 4, you get nu's. You get non-orientability. Okay. Here is the proof for those off-diagonal entries. The only non-trivial entries are off-diagonal, so we shall focus our effort on that. So let's try to see what happens if I add, for example, sigma g and nu g prime. Yeah? I cannot push. Oops, excuse me. So you want to take the connect sum of a surface like this, which is sigma g, and then just connect sum with a surface like this, which is mu g prime. So they are supposed to be g of those handles and g prime of those movie strips. So how do you calculate that? I'm going to continue that calculation over here. So if you can go from there to here, that last picture is supposed to be homeomorphic to the next picture. So let's put that picture in a more suggestive form with handles. You have those handles, g of them, and then those movie strips, g prime of them. So that's the surface that we have to understand. Which surface is this? Well, exactly the same argument as before, but now we have lots of handles. Let's grab this handle, for example, and slide it and go around the movie strip once and come out. Okay? Each time I do that, I convert this handle from outside to this strange climb type handle that goes from outside to inside. Exactly by this process. So after you slide this, in the course of which you are not changing your homeomorphism time, it's always the same surface, I'm just deforming it continuously without tearing anything, you end up with this picture. Okay. Now, how many of these handles are there? G of them. How many of those movie strips are there? G prime of them. And let us look at the composition of the picture, just like so. Okay. So each of these bits is a Klein bottle. But the Klein bottle, according to the fundamental lemma that we have, example 20 that we discussed, and according to the lemma, splits into two movie strips. So I can replace each of these strange Klein-esque handle by two movie strips, and the result is going to be, well, you have already understood what's going to be. Those movie strips just survive without being touched, and each of these will give rise to two movie strips. So how many pairs of these are there? Well, there are G of them, so there are two G of them, and here there are G prime of them, hence that result. Okay? So you see how wonderful this strange but useful notation is. I mean, this is supposed to be this complicated operation of taking out the whole and then gluing back a movie strip by identifying the boundary circle of the movie strip, the boundary circle of this whole. It's a very complicated and rather mysterious operation, which, as I keep saying, you cannot do in our three-dimensional space. But you can nonetheless calculate and have a complete mathematical understanding of what happens if you add and put together various surfaces. You start seeing, thanks to geometry and topology, things that you cannot physically and in ordinary life see. Your vision is now being expanded to better things. Okay. So that's what it is. Okay? Now, a little remark before we close this section. Remark 23. We decided in that table of connected sum as well as in the classification scheme to try to reduce everything to just sigma or n. In other words, express everything in terms of handles or everything in terms of movie strips. And we didn't want to have a mixture of these two. However, another approach is possible. Maybe, you see here, initially you had only G prime movie strips, but at the end we have so many movie strips. Maybe you don't like movie strips. Yeah? In that case, let's minimize the number of movie strips. Well, here's an idea. If you have two movie strips, you can combine them to make a Klein bottle. Okay? And if you have a third movie strip, I can slide that Klein bottle around and make it into a handle. In a way, the reverse operation to what we have done. So we may wish to minimize in each representation of a surface the number of movie strips, in which case what you get is as follows. Sigma G, of course, looks like G handles attached to a sphere, so that's the picture of sigma G. But what about this picture of N? It turns out that if you have NG where G is odd, you have a picture like this. A lot of handles together with just one movie strip. That's N odd. Why is this? Because if you have an odd number of movie strips, you can combine them 2 by 2, but there'll be one left over. Each combined pair of movie strips will become a Klein bottle. Klein bottle, which you pull and slide it around the remaining movie strip, will become a handle, and so you get all those handles plus the remaining movie strip. If you have an even, then you have this standard form for minimizing the movie strip. just two movie strips and any number of handles. Again, you combine all the movie strips pairwise, but you have to leave two at the end. Why? Because you see, if I combine these to make a Klein bottle, then there is no more that magic zone left over which to slide the Klein bottle and make it in the handle. I have to leave this patch of magic land where you go in and come out on the other side. That's a movie strip. So in order to keep this reversal process, I have to leave at least one movie strip, but that makes me obliged to leave two at the same time. So you get this standard form. When you have n odd, the standard form is number of handles plus one movie strip, and even number of handles plus two movie strips. That is a digression. You don't have to worry too much about this.
Why we need to leave the reverse direction? Why we need to give the reverse direction, which to return back? Why I leave two?
Why do I leave two?
Yeah,
okay, suppose that you say there are two movie strips left. You say, I know what to do when I have two movie strips. I can combine them to make a Klein bottle. So Klein bottle, which starts outside and somehow connects back inside. And then you want to say, oh, I don't like this Klein bottle. I want to turn it into a handle. Yeah? So what I mean is start from here and go back there. But you see, in order to go from inside to outside, outside, inside, you need one movie strip.
I asked, I know this, but I asked why you need to go the reverse.
Oh no, okay, so at this stage, if you combine, you can leave it in the form of a bunch of handles plus one Klein bottle. That's okay too. Yeah. But I'm just saying, if you want to represent all the surfaces in terms of handles and movie strips, so in particular no Klein bottles, and you want to minimize the number of movie strips, this is the standard form. You might want to represent things in terms of Klein bottles and handles and so on. That's another matter. Okay? Good. Any questions about this, this whole story? You have now covered the whole of topology with some sort of results admitted, but essentially all the main ideas of the topology of dimension 2. You know all the surfaces that can exist in the universe, all the compact and without boundary surfaces, and you know how to manipulate them, you know how to cut and paste them, and so on. In particular, you have learned the theory of surgery. By the way, the surgery theory, of which I presented to you, the two-dimensional version, exists in higher dimensions as well. It's much more interesting, a little more difficult, and there is a whole sort of subject which was built in the 1960s and 70s that was very powerful in classifying manifolds by cutting and pasting, sliding handles, and things like this. This is the lowest dimensional example, which is already interesting. There was an incident where in a bookstore in New York, there was a book on mathematical surgery, surgery on simply connected manifolds, and a student went to buy this and couldn't find it in the mathematical section and finally found it in the medical section. Let's then. Okay. Good. Okay, we shall now start the second chapter of this course entitled Isotopy. You might wonder what isotopy is. In a more familiar term, it is how to deform various objects, the theory of deformations. We have used the idea of deformation already in the beginning when we discussed solving problems by deformation in terms of examples. And we also had some sort of deformation arguments, so first sliding handles and so on. But now we shall discuss systematically how to deform various objects in all dimensions. And in particular, the relationship between deformation and dimensions of various spaces. We will now learn the object of this section, how to move submanifolds inside an ambient manifold. Remember that the manifold is just a geometric figure of some dimension. So if you have some sort of space or manifold, and you have some geometric figure inside, that's called a submanifold. How do you move it around the manifold? And you'll see with various examples what we mean. But to begin, let's discuss really the simple but essential case. On the plane R2, if you have two lines, how are they positioned with respect to each other? Do they cross or do they not cross? Two lines on the plane. What do you think? Well, they cross. And, you know, somebody very alert like Acham Yeresh will say that, oh, but there are cases when they don't cross, when they are parallel. But usually they cross. This is a stable picture, and only exceptionally are they parallel. So, two lines, we say generically. This means usually, stably, you know, except in really unlucky circumstances, two lines generically intersect in a point. Two lines have dimension 1 and dimension 1 each. The point has dimension 0. Do you see that 1 plus 1, yeah, minus 2 is 0? It turns out not to be an accident. Okay. There are cases, lines that do not intersect. As you are going to complain, the picture is the parallel case. But these cases are degenerate. I'm not defining what generic and degenerate are. I'm hoping that you understand, you have an intuition about what these things are from the examples. Degenerate. So they are, if you like, exceptional, unstable, in the sense that if you perturb it a little bit, they immediately become non-parallel. Yeah? And unlucky, probability 0, and so on and so on. So generically, they intersect in a point. Good. Let's go on to R3. In R3, a line and a plane what do they look like? And a line like this intersect in a single point. Okay, there might be cases when they're parallel, but that's going to be quite unlucky. So a line and a plane, line has dimension 1, and plane has dimension 2. Intersect in a point which has dimension 0. Again, you note that 1 plus 2 minus 3 is 0. How about then a plane and a plane? What do you think? If you have two-dimensional planes inside R3, how do they intersect?
They can intersect by
Intersect along the line. That line is a one-dimensional intersection. So, in general, if you have a k-dimensional subspace and an l-dimensional subspace in an m-dimensional space, how do they intersect? What's the intersection dimension? Something like that. Okay, we all have our conjectures. I'm very happy to hear you say so. Okay, so but in this case, two planes generically intersect in a line. Yeah, we all understand that. And the picture that I shall draw is this kind of picture. Oops. Oops. Yeah, so that's the intersection. Okay. Good. And of course, here again, there are degenerate situations. You can have a plane and a line which are parallel to each other, or maybe plane and a line which is inside a plane, or two planes that are parallel to each other, or two planes that coincide. They're just exactly on top of each other, and so on. In that case, of course, the intersection is empty. Intersection is just a line. Intersection is empty here, and the intersection is the plane itself. So in all those cases, you don't have the conclusions that we have, but those are degenerate cases. Good. Let's then summarize what our conjecture, theorem 1. Why are we back to 1? Because it's a new chapter. Let K and L inside M be submanifolds inside the manifold M, or if you like, subspaces inside the space M, and so on. You give them the meaning you like. And let us call this strange number dimension of K plus dimension of L minus the dimension of M. This number, which can be positive, negative, or 0, we shall call the overflow. And we'll see in a moment why it's called the overflow. This term is not standard. I invented this term, and we shall use it in this Ames course. Well, why do we call it overflow? Here is why. You see, the ambient dimension, the box in which, the space into which we are trying to fit K and L, has dimension M. Yeah? It has a certain dimension. Now, it's very intuitive that if you try to put a very large K and very large L, they will not be able to fit separately. Yeah? They'll have to start crossing, because there isn't enough space in the ambient space to fit those, to accommodate those submanifolds. So how much overflow is there? That's exactly this. So you try to put K and L together, and this is as much room as there is. And if you have too much, again, in a too little space, then you overflow. If you have plenty of ambient space and you're not putting very much, then you have plenty of space. That overflow is still negative. In other words, negative overflow, that means there is no overflow. Okay? So this is how much overflow you create how much dimension overflows when we try to fit force fitting K and L into M. Yeah, that's the intuitive interpretation. That's why it's called overflow. It might be a little strange to think of negative overflow, but when it's negative, that means there's still room. You have still space with that. Now, okay, I shall have to go there. I'm sorry. I like to state a theorem on the same blackboard, but sometimes I mistime myself. Okay.